Welcome back to GLS4OM. I'm going to let you sort of get started reading that comic while I get the pencil set up. All right, we are continuing our work in Unit 9, Matrices. Matrices is going to be particularly important for any of you who will be taking linear algebra in your first year university program. So we have calculus as a first year math course, and we also have linear algebra as a first year math course. And you're going to do a lot of work with matrices and some things that you did with in the vectors course in MCV 4U1. So taking a look at this comic, Jason and Marcus. So this is Jason. Jason wants to know if you saw ultraviolet bulb. Got what? Excuse me? What about regular violet bulb? No. Blue bulb? No. Green bulb? No. Yellow bulb? No. Orange bulb? No. Rats. Okay, I'll take a red bulb. And then I was hoping for something a little higher energy. And Marcus says, well, at least it's an infrared bulb. So that's for the science geeks out there who understand wavelengths and wave theory. All right, moving forward, what are we doing in Lesson 2? So in Lesson 2, we're going to review it. Maybe a review. If you took calculus in first semester, definitely will be a review. I'm not certain, given distance learning, if this was able to be presented in your current calculus classes for those of you who are taking it now. But it's an algorithm for solving a system of linear equations by using matrices. What's nice about it is instead of working with all of the variables, we just work with the coefficients and the constants. So we're going to create what's called an augmented matrix, and we're going to combine the coefficient matrix with the constant matrix. So the coefficient matrix is obtained by using the coefficients. So 1, 2, 3. From the first equation, 3, 4, 7 from the second, 6, 5, 9 from the third, and then the constant matrix is 0 to 11. So coefficient matrix, just the coefficients, the constant matrix, just the constants. The augmented matrix is written A, we got this vertical bar, B is written like this. We are separate the coefficient matrix on the left from the constant matrix on the right by using a vertical bar. So that's the matrix we're going to be working with, the augmented matrix. So to perform Gaussian elimination or row reduction on the matrix, we're going to use what are called elementary row operations to modify the matrix. And the objective is to fill the lower left-hand corner in Gaussian elimination, the lower left corner with zeros. That's what we're going to be trying to do. And I'll explain how to do that in a few minutes. 3 types of elementary row operations are: you can swap 2 rows below the pivot, and I'll explain what the pivot is when we get to one, or 2 columns to the right of the pivot. You don't want to make any shifts above or to the left of the pivot because it's going to undo your hard work. You can multiply a row by a non-zero constant, and you can add a multiple of one row to another. So those are the 3 things you can do. And before we get there, I just need to do some definition type stuff, because what we're going to be after is row echelon form. Now, what does row echelon form mean? If we're talking about a matrix. So all rows that consist entirely of zeros get written at the bottom of the matrix. That one's easy to understand. And this one might be a bit more challenging. And any 2 successive rows, that is, one below the other, that are not or do not consist entirely of zeros, the first non-zero number in the lower row has to occur farther to the right. So it cannot be underneath it. It has to occur farther to the right than the first non-zero number in the row directly above it. So look for the first non-zero element in one row, go down, find the next non-zero element in the row below it, and that needs to be to the right. And why echelon? It turns out echelon, French, is a step-like arrangement of troops. And if you're in echelon form, you would resemble a set of stairs. In French, it actually literally translates to rung of a ladder. But in the military, it was a step-like arrangement of troops. So something like this, or something like this. That's why this is referred to as row echelon form. So what you're going to do now is you're going to think about the following matrices which are in row echelon form. If they aren't, see if you can use an elementary row operation to put them in the correct form. Now, I think we're going to do all of these at once, and I'm just going to remind you what it means to be in row echelon form. If you are in a row entirely of zeros, then you need to be at the bottom of the matrix. And if you're not a row of entirely zeros, then you want to take two of those successive rows. The first non-zero element in the lower row must occur to the right of the first non-zero element in the row above it. All right, our first time to ponder pause. All right, resuming to take this up. Hopefully you took time to think this through. So we'll take a look. There isn't a row entirely of zeros, so I'm just going to go through and take a look at this one. So there was the first non-zero element in this row. It was right here. And then I go down to find the first non-zero element in the row below it, which happens to be right here. And notice this does not occur to the right of this one. It needs to be shifted over there. So this would not be in row echelon form because that too violates it. I'm just going to undo that arrow I drew. So what are we going to do? I'm going to have to zero this out. How will I zero it out? I'm going to zero it out by multiplying row 1 by -1 and adding it to row 2. So -1 times 0 is 0 plus 0 is 0. -1 times 2 is -2 plus 2 is 0. -1 times 3 is -3 plus 4 is 1. -1 times 0 is 0 plus 0 is 0. So this is what I did to replace row 2. I replaced row 2 with negative row 1 plus row 2, and now we are in row echelon form because the first non-zero element in the second row is here, and notice it is to the right of the first non-zero element in the first row. And the first non-zero element in the third row is to the right of the first non-zero element in the second row. And notice how we are creating a staircase, which is why that is called row echelon form. All right, let's take a look at this next one. So we go down to this row, we look at the first non-zero element, and it is definitely occurs to the right of the first non-zero element in row 1. So the first non-zero element in row 2 occurs to the right of the first non-zero element in row 1. And then the first non-zero element in row 3 is occurring to the right of the first non-zero element in row 2. So this is in row echelon form. All right, so if we're going to take a look at this one, first off, I guess we're just going to say, I don't even need to say that row 2 violates row echelon form, right? There are no non-zero elements in that row. I guess what we can say the bigger problem is this row needs to be at the bottom of the matrix. So let's move that to the bottom of the matrix. And now let's take a look. The first non-zero element in row 2 is occurring to the right of the first non-zero element of row 1, and a row of zeros on the bottom. This now satisfies the definition of row echelon form. And now taking a look at the last one, again I've circled the first non-zero element in row 2. It is occurring to the right of the first non-zero element in row 1. And the first non-zero element in row 3 is occurring to the right of the first non-zero element in row 2. So row echelon form. So the two that were directly in row echelon form were the second one and the fourth one, and we needed to manipulate the first and the third to get them into row echelon form using elementary row operations. All right, so now what we're going to do is just sort of practice reading this. Let's say this was reduced to this state. What I'd like you to do now is tell me what the solution would be, and we can presume that this is x, and this is y, and this was z. Again, a time to ponder pause. Resuming to take this up, from the top row, I'm going to get negative x equals -4. Technically, it would be negative x plus 0y plus 0z equals -4, but I'm not going to write those. Negative x equals -4, so x is 4. Well, the bottom row is telling me that 0x plus 0y minus z is 2, so I'm just going to write negative z is 2, so z is -2. And now the middle row is telling me 0x plus y plus 2z is 4. So working with y plus 2z is 4, I can back substitute the z of -2. Get y plus 2 times -2 is 4. 2 times -2, -4. Bring it over, negative 4 becomes positive 4, and 4 plus 4 is 8. So the solution to this system is y equals 8, z equals negative 2, and x equals 4. All right, a student has used elementary row operations on an augmented matrix, and when they were finished, they came up with this matrix below. Explain whether or not this matrix is in row echelon form, and then explain why there is no solution for this system of equations. Again, a time to ponder pause. All right, resuming to take this particular one up. So let's take a look. The first non-zero element in row 2 is right here, and of course that is way to the right of the first non-zero element in row 1, and of course the row of zeros is on the bottom. So this is in row echelon form. Now, why is there no solution to this system of equations? So this row is telling us that 0x plus 0y plus 0z is negative 3. And of course, there are no triplets, x, y, and z, that would satisfy that. Any x and y and z we pick and we substitute into the left-hand side is going to give us 0. 0 times a number plus 0 times a number plus 0 times a number is 0. And 0 would not be equal to negative 3. Maybe I'll put a not through that. So 0 is not equal to negative 3. So there won't be any solutions. So that row says no solutions. The bottom row says 0x plus 0y plus 0z equals 0. All triplets, anything we pick for x, y, and z, any ordered triplet will satisfy this equation because 0 is always equal to 0. So this row says infinite number of solutions. This row says no solutions, and no solutions will always trump an infinite number of solutions. Okay, hopefully this is making sense to you. Big idea, definition of row echelon form, and we just talked about interpreting a matrix that's been reduced, figuring out what the solutions are. All right, what you're going to try now is to use Gaussian elimination. So if you've already seen Gaussian elimination, get started. Pause, get started, and figure it out. If you haven't seen Gaussian elimination, then maybe what you want to do is not pause and watch me work through this one, and then you can try the next one. Again, a time to ponder pause. All right, resuming to take this one up. So I'm going to imagine this one first because we want our pivot to be 1. And we're going to use the pivot. And again, we're just going to be coming down the diagonal. And we want to make these pivots. Now this one only is going to be a 2 by 2 matrix, so we would only have to do this twice, but we want the pivot to be 1. And the fastest way to get this first pivot to 1 is to simply write the second equation first. So 1, 2, and the constant negative 6. Your coefficient from this equation here, 2, 1, and negative 9, and maybe you want to track that this is x and this is y. Very important to do that if you decide to solve this, that what you want to do instead was swap columns, because we could have done a column swap, left this the way it was, and we could have written the y column first and the x column second. I normally don't write anything above the columns unless I do a column swap. So what are we going to do now? We're going to use this pivot to zero out the elements below it. So right now what's below it is a negative 2. So if we multiply this element by negative 2 and add to that, we'll be able to zero this out. So we now generalize that relationship. We say that I'm going to replace this row 2 up here with a new row 2 by doing this elementary row operation. I will multiply row 1 by negative 2, and then I will add it to row 2. So I'm going to show you how that would work. 1 times, let's do it this way, negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times positive 2 is negative 4, and negative 4 plus 1 gives us the negative 3. And now onto the last one. Negative 2 times negative 6 is positive 12, and positive 12 plus negative 9 is positive 3. That's how we determine this. Need to work carefully when you're doing this because it's really easy to screw something up here. I would just double check, do that twice. So let's do another check. Negative 2 times 1 plus 2 is 0. And negative 2 times 2 plus 1 is negative 3. Negative 2 times negative 6 plus negative 9 is 3. So that's worked out correctly. And now, next thing we need is I need this pivot. I need it to be 1. So what I'm going to do is I'm now going to adjust row 2 again, and I'm going to replace row 2 with row 2 divided by -3. So take the old row 2, which was here, divide it by -3 and get your next row. So 0 divided by -3 is 0. -3 divided by -3 is +1. +3 divided by -3 is -1. And now, why did I do that? Because I need my pivot to be +1. When we do this elementary row operation to zero out the elements above it, actually I suppose maybe I shouldn't have done that because I said I was doing Gaussian, so let me just pause for a sec. Alright, so resuming, I am doing Gaussian elimination, and this next matrix down here is actually Gauss-Jordan. So I'm going to put a line through that. We shouldn't do that. I'm zeroing this one out. We'll do that in the next lesson tomorrow where we do Gauss-Jordan. So Gaussian elimination, we're just going to try and make this one is 0. And now I've made this one my 1. So I now can see that y is equal to -1. And then I back substitute. The next row tells me that x plus 2y is -6. So x plus 2 times -1 is -6. That becomes x minus 2 is -6. Bringing that over, we get that x is -4. We'll see the advantage tomorrow of doing Gauss-Jordan is that we don't need to do any back substitution. All right, so I've explained and shown to you how Gaussian elimination would work on a 2x2. The next question you're going to do is Gaussian elimination on a 3x3. And again, a time to ponder pause. All right, so resuming to take this up, you sort of have some decisions before you begin. I wouldn't put this row first, the way as it is, because the pivot would not be 1 here. So you have some options. You could write this row first, as I have done. You could write this row first, or maybe you want to write this column first. Or if you want to rearrange the equations and the columns, then you could always put column Z first. All right, so what I chose to do instead is to just put this equation first. So 1, 1, 1, constant 2. Moving on to my next equation here. Oops, not over there. I did it over here for starters. So 1, 1, 1, constant 2. Then I put this equation. We have 1, 0, 1, 0. There's no y here, and the constant is 0. Then the top equation gives us 2, 1, 2, 2. So from here to there. All right, now notice my pivot is 1. So I'm going to use that pivot to zero out the elements in this column that are below it. So how will I do that? To zero out this, I'm going to need to do negative row 1 plus row 2. So I'm going to replace this row 2 with a new row 2, and I will find that row by doing negative row 1 plus row 2. For row 3, what I'm going to need to do to zero this out is I'm going to have to take the multiple of -2 times row 1 and then add that to row 3 to zero it out. So let's handle this one first. If I do -1 times 1 is -1 plus 1 gives me the 0 here. -1 times row 1, that's -1 plus the 0 is -1. -1 times row 1, so -1 times 1 is -1 plus 1 gives me a 0 here. Negative row 1, so -1 times +2 is -2 plus 0 is -2. So that's how we obtain the new row 2. To obtain the new row 3, I'm going to need to multiply each element in row 1 by -2 and then to add to the corresponding element in row 3. So -2 times 1 is -2 plus 2 gives me a 0. -2 times 1 is -2 plus 1 gives me a -2 here. -2 times 1 is -2 plus the 2 here gives me a 0 here. -2 times 2 is -4 plus 2 gives me a -2 right there. And we probably can now see that these two rows are identical, so one of them is going to wipe out, but I'm just going to continue showing you how Gaussian elimination works. So what we would do next is we would want to make this pivot 1. How am I going to make that 1? Simply by dividing this row 2 by -1. or multiplying it by -1. So I've noted I will find this new row here by multiplying the old row 2 by -1. 0 times -1 is 0. -1 times -1 is +1. 0 times -1 is 0. And -2 times -1 is +2. And then we're going to use this as the pivot. And what we're going to attempt to be doing now is to zero out this value right here. How will I do that? This I'm going to cross off. We don't need that to be written there. All right, so what I'm going to do here is I'm going to need to just simply add row 2 and row 3 to make that happen, right? Because an add here will zero that out. So I've noted to create my new row 3, I will add row 2 and row 3 together. So 0 plus 0 is 0. 1 plus -1 is 0. 0 plus 0 is 0. And 2 plus -2 is 0. So that's how we arrived at this matrix. And now what's this matrix telling us? Because now we are in row echelon form, and we're not doing Gauss-Jordan elimination, we're doing Gauss, so we're finished now. So we would use the last row to tell us something. Now the last row is really telling us there's an infinite number of solutions. So if you've done this already in calculus, you know that these three planes are meeting in a line. They're meeting in the equation of the line. So I'm going to find the equation of the line now. So this row is telling me that 0x plus y plus 0z is 2, i.e. y is 2. The top row is telling me that x plus y plus z is 2. However, we know that y is 2, so this is just going to give us that x plus z needs to be 0, and that's going to simplify down to that z is -x. And now typically what we do is we find a parameter to write this in. So I'm going to choose t for my parameter, and I'm just going to choose, I'm going to let x be t. But I'm going to write it as 0 plus t so that you can see where I'm going to get the coordinate for my point from. I'm now going to rewrite this equation here as 2 plus 0t, because I want you to see where I'm getting my direction vector from. Remember, the t's are going to be our direction vector, and the constant is going to give us the coordinate for our point. And now for the z coordinate, I'm going to write 0 for the point and -t. So 0 minus t. So my point coordinates, I'm just going to change the color of my pen here. My point coordinates would be 0, 2, 0. So I wrote that down, 0, 2, 0. And my direction vector is going to come from here, 1, 0, -1. So my direction vector is plus t times 1, 0, -1. And remember, we have to note that t is any real number. So these three planes are intersecting in the line, in the equation of the line in vector form right there. My little vector symbol across there, 0, 2, 0, plus t times 1, 0, -1. All right, so what we're going to do next is now we're going to try one more of these, and this one is going to be a system of 4 unknowns and 4 equations. So I'm going to read, so this part is from Harry Potter and the Philosopher's Stone, this part that I'm quoting up to here, and then I'm going to add to it. So I'm the Hogwarts sorting hat, as you can plainly see. It's my job to place you in the house that you should be. You might belong in Gryffindor, where dwell the brave of heart. Their daring nerve and chivalry set Gryffindors apart. You might belong in Hufflepuff, where they are just and loyal. Those patient Hufflepuffs are true and unafraid of toil. You might belong in Ravenclaw, if you've a ready mind, where those of wit and learning will always find their kind. You might belong in Slytherin, you'll make your real friends. These cunning folks use any means to achieve their ends. All right, I'll tell you, now this is Hanta adding to this. I tell you now to try me on, but I am in a flap. I'm not too good at math, even though I am a thinking cap. There are restrictions on the numbers in the houses you can go. Gryffindors and Hufflepuffs have the same numbers, as you know. Double those in Gryffindor, plus those in Slytherin, are always a match to thrice the number of students who are in the Ravenclaw batch. Obviously that stanza needs a little bit of work, so it flows better. 10 more than 4 times those who find Slytherin home is the same as Ravenclaws counted twice added to those with the Gryffindor name. 100 students belong in either Slytherin, Ravenclaw, or Gryffindor. Find how many students in each house for Professor Dumbledore. So I think where we will start is read each one of these little stanzas. I think that is the proper English term for this. Each one of these will give you an equation. So I think start with the equations and a setup of your initial matrix. Again, a time to ponder pause. All right, so resuming, just to make sure that you have the correct equations before you try Gaussian elimination. So from the first stanza, we get G is equal to H, Gryffindor is Hufflepuff. From the second stanza, we get 2 Gryffindor plus Slytherin is 3 times Ravenclaw. From the third stanza, we get 4 Slytherin plus 10 is 2 Ravenclaw plus Gryffindor. And from the last stanza, we get Slytherin plus Ravenclaw plus Gryffindor is 100. Now, I'm going to rewrite these. I'm going to use my variables that I have there. Again, we need all the variables on one side and the constant on the other to go to the matrix. So G minus H is 0. 2G minus 3R plus S, I'm going to write it in alphabetical order, is 0. G plus 2R minus 4S is 10. Again, writing this in alphabetical order. Just bringing the 4S over to this side. And on this case, G plus R plus S is 100. This pivot was already 1, so I'm just going to write them in the order I see. Maybe above this, I will note that this is G, alphabetic order, H, R, and S. So 1, negative 1, 0, 0, 0 from this next equation. 2, 0, negative 3, 1, and 0 from this next equation. Remember, none of these 3 equations have H's. It's going to be 1, 0, 2, negative 4, and 10. And from this last equation, it's 1, 0, 1, 1. 100. And what you're going to do is, I've already circled the first pivot for you. What you are going to do is use this pivot to eliminate this element here, here, and here. And obviously you have to update all the other elements. And then the next thing you will do is you will want a pivot to be 1 here. You can accomplish that if you need to by row swaps below this row or column swaps to the right of that. So anything in this area. And then just continue. So you would get this to be a 1, 0's below that. This would become a 1, you'd want a 0 below that, and then you'd want to make that a 1. That's how Gaussian elimination works. So our final time to ponder pause so you can finish that off. All right, resuming to take this one up. So in order to zero this out, I'm going to have to do negative 2 times row 1 plus row 2. In order to zero this out, it's going to be negative row 1 plus row 3. In order to zero this out, it will be negative row 1 plus row 4. So walking you through this, if we multiply this by negative 2 and add, we will get 0. Multiply that by negative 2 and add the 0, we get 2. Multiply this by negative 2 and add that, we get negative 3. Multiply this by negative 2 and add that, we get 1. Multiply this by negative 2 and add that, we get 0. Our replacement for this row is multiply this by negative 1 and add to that, we get 0. Multiply to negative 1 and add to that, we get to 1. Multiply by negative 1 and add to that, we get 2. Multiply by negative 1 and add to that, no change, negative 4. Multiply by negative 1 and add, no change, that stays at 10. And on the last row, same idea, multiply by negative 1 and add. So multiply by negative 1 and add, we get 0. Multiply by negative 1 and add, we get 1. Multiply by negative 1 and add, no change. Multiply by negative 1 and add, no change. Multiply by negative 1 and add, no change. So we've used this pivot right here to zero out the elements below it. And what we now need is I need a pivot. This would be the next pivot lining up. I'd need this to become a 1. But if I make this a 1 by dividing by 2, I will now have to work with fractions. I would prefer not to work with fractions. So maybe I'm going to do a swap. This row looked nicer to me. Again, I could have swapped row 2 and row 3, but I'm going to choose to swap row 2 and row 4. So I replace this row with row 4, and I replace this row with row 2. That's the only changes I made in this matrix. And now I have my nice pivot of positive 1 here. So again, we're going to zero out what's below it because we're doing Gaussian elimination. So in order to zero this out in row 3, I'm going to have to do negative row 2 plus row 3. In order to zero this out, I'm going to have to do negative 2 row 2 plus row 4. So row 3, negative row 2 plus row 3. Row 4 will become negative 2 row 2 plus row 4. All right, so let's deal with this one first. So I'm going to multiply this by negative 1 and add. This still stays 0. Multiply by negative 1 and add, we get 0. Multiply by negative 1 and add, we will get 1. Multiply this by negative 1 and add, we get negative 5. Multiply this by negative 1 and add, we get negative 90. And now we had said to zero out and handle row 4, we're going to need to multiply this by negative 2 and add. So negative 2 times this plus this is 0. Negative 2 times this plus that is 0. Negative 2 times this number plus that is negative 5. Negative 2 times that plus that is negative 1. Negative 2 times this plus that is negative 200. And notice how nicely our next pivot is already lined up beautifully for us. It is a 1. So I simply need to zero this out, and I will zero this out by multiplying row 3 by 5. So 5 times row 3 plus row 4 will zero this out for us. So that's what I noted over there. And then working my way through this, I'm now going to do 5 times this plus this is 0. 5 times this plus this is 0. 5 times this plus this is 0. 5 times this plus that is negative 26. 5 times this plus this is negative 650. And then what I would like to do is just make this 1. And in order to make that 1, I'm going to divide row 4 by negative 26. So that's what I've noted over there. Row 4 is row 4 divided by negative 26. We're going to get 0, 0, 0, 1. And when you divide that by negative 6, you get 25. So now I'm completely in Gaussian form. Notice I'm just coming across that diagonal there. The diagonal is all 1s, and everything below the diagonal zeros, and we've got that sort of echelon step thing happening. That's how Gaussian elimination works. So now what we do know is we know that the last column, which was our letter S, is 25. So S is 25. Back substitute to the next row, that tells me R minus 5S is negative 90, so that's what I've written there. Plugging in a 25, we'll get R minus 5 times 25. R minus 125 is negative 90. That gives me R is 35. That's the second value I found. Then back substitute in the row above that. That row tells me that H plus R plus S is 100. So H plus R plus S is 100. H plus R is 35 and S is 25, so that gives me 60. 100 minus 60 is 40. H is 40. They did say in the poem that G and H were equal, so I could simply go to G is 40 here. However, in case we didn't know that from the original matrix, I'm just going to take this row that says G minus H is 0. Back substitute the H of 40. G minus 40 is 0, which of course gives me G is 40. So those were the correct answers to that little riddle I gave you here. You've now solved this for Professor Dumbledore. We do know that there are 25 students in Slytherin, 35 students in Ravenclaw, and 40 students each in both Hufflepuff and Gryffindor. All right, that brings us to the end of this lesson on Gaussian elimination. Hopefully you found it useful. Going to be particularly useful again for those of you taking linear algebra. If you made it to the end, once again, thank you. Don't forget to smash that like button. And as always, take care and stay safe.